Okay, hi everyone. All right, thanks for coming. We come to seminar today. We are super lucky to have from Kyoto University in Japan, Professor Kosuke Ito. Ito-san got his PhD in 2011 from Kyoto University. He spent 1 year as a postdoc working with Chunche Wu at National Taiwan University in Taiwan. 2 years as a postdoc at JAMSTech. It's in Yokohama, right?
Yes, Yokohama.
And then 9 years as a professor at the University of the Ryukyus, and that's Okinawa. And then he has since changed to Kyoto University, where he's an associate professor of severe storm and extreme weather at the Disaster Prevention Research Institute. Ito-san has received the Shono Award from the Meteorological Society of Japan, the Sola Paper Award from the Meteorological Society of Japan. He was Professor of the Year in Natural Science at the University of Ryukyus, and he's also, with the team, got the Excellent Paper Award from the Seismology Society of Japan. So, he's going to talk about the three-dimensional Fujiwhara effect, right?
Okay, thank you very much. Nice introduction, Dave. So, I'm happy to be here. My name is Kosuke Ito, working at Kyoto University, Japan. Today, I'd like to talk about the three-dimensional Fujiwhara effect. Actually, I learned a lot from the paper of Dave since I was a grad student. And I think I met Dave in maybe 2012 when I was in Taiwan, National Taiwan University. Yeah. Since then, we had a good relationship. And last year, I invited him to have our 4-hour seminar in Japan. And I think it's my turn. Not 4 hours, but just 1 hour. But I hope you will enjoy my talk today. Okay, so I'm doing a lot of kinds of works mainly related to tropical cyclones. So upper left movie shows the Japanese aircraft mission. Eyeball penetrating aircraft missions have been done in the last 8 years. We penetrate the eyeball by using the G4, Gulfstream 4 aircraft. So this is kind of interesting work I'm doing. And also, I'm interested in the data simulations and the development of atmosphere-coupled, ocean-coupled model, and historical tropical cyclone data rescue is another research topic of me. But today, I'd like to talk about a more tropical cyclone track. Of course, tropical cyclone track is very important. If the tropical cyclone track forecast fails, track forecast, intensity forecast or rainfall forecast are less meaningful. So I think the track forecast is very important. Nevertheless, the fundamental understanding of tropical cyclone track forecast, a fundamental understanding of tropical cyclone motion is not, actively investigated in the last 30 years. Partly it is because many people believe, the tropical cyclone track is already understood. They are related to, steering flow and sometimes, beta gyre effect. But I say no. So I'd like to talk about more, new stuffs on tropical cyclone track studies today. Okay, so this figure shows the track forecast errors operated by Japan Meteorological Agency in the last 40 years. As you can see, the errors has been decreased more than half in the last 30-40 years. But nevertheless, you see the forecast errors, track forecast errors is around 200 kilometers on average for the forecast time of 72 hours. So still we need to improve the track forecast. Another thing I'd like to stress here is, tropical cyclone motion is related to the rainfall amount. If you are living in some location, when a tropical cyclone moves very slowly, total rainfall amount becomes so huge. So this figure shows, the x-axis indicate the translation speed of tropical cyclone near landfall time, and this y-axis indicates the maximum wind speed. And the size of this each circle indicates the maximum total precipitation observed. So you might think, the stronger tropical cyclone gives large amount of precipitation, but it's not always the case. When a tropical cyclone moves very, very slowly, it's tremendous in terms of the total rainfall amount. So we need to care about tropical cyclone motion. Okay, so this is a top 5 or worst 5 in terms of the track forecast errors. So these 5 conditions are the initial condition that yielded the worst track forecast recently. You notice that, okay, here is this tropical cyclone indicated by the red star was a target tropical cyclone, but you notice that another tropical cyclone or some another vortex are located nearby. So something happens when the other tropical cyclone exists. Okay, so this is the statistics. We stratified a data set according to the existence of the binary counterpart tropical cyclone nearby. In case there is no counterpart tropical cyclone nearby, in that case, tropical cyclone track forecast is much better. But if nearby tropical cyclone exists, in that case, track forecast error tends to be large. So in that sense, we need to understand what happens when 2 tropical cyclones coexist. Okay, so let me explain. Let me begin with the conventional Fujiwhara effect, where that is related to the tropical cyclone motion, binary tropical cyclone motion. Okay, so this person is Dr. Sakuhei Fujiwhara, who was a Director General of Japan Meteorological Agency during the World War II. And actually he studied in United Kingdom 1920. So he did a lot of pioneering works on the vortex election. The most famous one is most famous results of him is the 2 cyclonic vortices rotate anti-clockwise around the center of them and get closer to each other. So this is the 2 vortices in a laboratory tank, and you see 2 vortices here, and you can see these 2 vortices rotate, anti-clockwise direction to each other, and then finally they get closer to each other, and finally they get merged like this. So this is what Dr. Sakuhei Fujiwhara proposed. So this effect has been called as Fujiwhara effect. Well, hi.
So I want to be clear.
Okay.
So the original Fujiwhara effect was not first about tropical cyclones.
No.
Wow, I had no idea. I've always thought it began with
Ah.
tropical cyclone motion. Thank you.
Thank you very much. Yeah. So this concept is not originally for tropical cyclone. Yes, of course, that's one of the applications is tropical cyclone motion. Okay, thank you. So this is an animation what we see in a non-divergent barotropic model. As I explained to you, binary vortices rotate anti-clockwise and get closer to each other through a vortex-vortex interaction. I think counterclockwise motion is easy to explain. For example, here, assuming two vortices here, vortex A and vortex B here, and the wind associated with vortex A is like this, counterclockwise, blowing, counterclockwise direction, and it makes the vortex B move to the north. And the wind associated with vortex B is blowing this way, and then it makes the vortex A move to the southward. So maybe more, precise calculation can be done through more, fluid dynamics, and I think that Dave talks about this kind of things, but this is a simple schematic explanation for the counterclockwise rotation of motion. Okay, so let me try to explain the approaching motion now. I think the approaching motion is a little bit difficult to explain, but let me try to explain it in a simple way. Okay, so assuming the vortex now has a size, so vortex regions, two vortex regions, and then okay, so we can consider the vortex at these 2 points. Well, at this green point, the vorticity is relatively larger because the vorticity is somewhat overlapped. And at this yellow point, the vorticity is relatively small compared to this one. And the wind is blowing in this direction. According to the advection of vorticity, and we assume that the vorticity is nearly conserved, and then we can expect that large vorticity is to the north of this vortex A center. And relatively small vorticity is transported to the south of the vortex A center. Now we revert the vorticity to the wind field, wind anomaly. We can get some anomalous wind field in this way. So it makes the vortex A approaching to the vortex B. So it is kind of a simple explanation how the vortex A approach to the vortex B. Okay, so far this is very conventional. Okay.
Can I ask question? So what will happen if you go to previous slide? What will happen if we have a larger vorticity on the left hand side than the right?
Okay. Thank you very much. Yes, of course, the impact from larger vorticity is smaller vorticity is large, and impact from smaller vorticity and larger vorticity vortex is very small. So maybe you can expect, but I think the basic quantity we can consider is a circulation. Integrated the vorticity. That's a very basic quantity we need to consider.
And at the end they will merge.
Right. But still, the motion of larger vortex is very small, and the smaller vorticity is moved larger. Okay. So that's the manner. Okay. So far I explained about the conventional Fujiwhara effect, but can you expect what will happen in three-dimensional model with diabatic heating? Here it is. This is an idealized wave simulation for binary tropical cyclone, initially separated by about 1,000 kilometers on an F plane. And there is no other disturbances than binary tropical cyclone, so it's very, very idealized situation. And sea surface temperature is 28 fixed, and then very simple heading. This is on an F plane. But the result is very different from what we had in the non-divergent two-dimensional model. At first, two tropical cyclones slightly moves anti-clockwise direction, but in later period, they are moving apart from each other, right? And then these colors indicate the simulated reflectivity. And you see that the more and more convection occurs outside from the counterpart tropical cyclone. So this is very interesting. And then as far as I investigated, nobody explains this phenomena. So we decided to investigate more. Okay, key question. What happens with our three-dimensional model? So again, this is a simulation setup. We employ the WRF, and the Corollary's parameter is fixed at 10-15 degree nose. And microphysics is WSM6 and no cumulus parameterization. And horizontal grid is 4 kilometers, sufficiently resolving the inner core dynamics. Domain size is about 5,000 kilometers each, and SST is fixed. No disturbances other than binary thesis, so very simple idealized simulation. And one parameter we changed is initial separation distance. Initial separation distance was 6 degree, 8 degree, 10 degree, 12 degree, something like that. And then for presentation purpose, we call it a DXX. For example, D0X means the initial separation distance of 8 degree or something like that. Okay, so this is a summary of the simulated tracks. If we put the binary tropical cyclone initially separated by 6 degree, the anti-clockwise motion was freely reproduced, and then they finally get merged as in a two-dimensional conventional Fujiwhara effect. But 10 degree initial separation or more than 10 degree separation, in that case, initially they tend to show some anti-clockwise rotation, but later on they tend to move away from each other. So very interesting. So to analyze what is going on in these systems, we employ the potential vorticity budget. I think most of you are familiar with potential vorticity, but basically vorticity concept is generalized, and it has much more conserving property. And by using potential vorticity budget equation, we can analyze tropical cyclone motion more. Tropical cyclone center can be regarded as the location of high potential vorticity. And so, for example, let me consider one tropical cyclone. Okay, so this is the inner core region. We expect the potential vorticity is much higher, right? When a tropical cyclone moves to the northward, high potential vorticity comes over here to the north of tropical cyclone. And then potential vorticity decreases to the south of the original center. And so that is the left-hand side of this equation. And if horizontal advection calculated in this term is explains the increasing tendency to the north of the tropical cyclone and decreasing tendency to the south, in that case, okay, we can make sure that the tropical cyclone motion can be explained by the horizontal advection, right? But tropical cyclone motion is not necessarily be solely explained by the horizontal advection. Other terms can impact on the tropical cyclone motion. For example, if there is the asymmetric heating to the nose of tropical cyclone, for example, convection actively occurred to the nose of tropical cyclone, in such a case, we can expect the genesis of potential vorticity beneath of the maximum heating location. So in such a case, potential vorticity is generated to the nose, so it makes the vortex move to the nose. This is another mechanism that makes the vortex move. Okay, so to analyze these terms, we can analyze which mechanism contributes to the tropical cyclone motion. Now, of course, friction is important in a boundary layer, but here I do not consider that. So just we focus on the 850 to 300 hectopascal. Okay, so this is the result of the potential vorticity budget analysis. Especially, we subtract the wave number 1 component of PV budget for the 10-degree initial separation distance at the time of 72 hours since the initial time. Okay, so left panel indicates the potential vorticity tendency in time. You can see the green colors here and the blue colors here. Excuse me. So you see that the potential vorticity increases in time in the south to southeast and decreases in the north and the northwest. So which means the tropical cyclone moves to the south or southeast. Okay, of course this is consistent both at the 500 hectopascal and 850 hectopascal, but the budget are different. Breakdowns are different in different levels. At 850 hectopascal, this PV tendency is almost explained by horizontal advection. So which means the wind makes the vortex move. However, in the lower troposphere, asymmetric diabatic heating control the tropical cyclone motion, which means the stronger convections in the south side, southeast side makes the vortex move. Well, I think somebody are familiar with the diabatic heating asymmetry, but I think some are not. So let me briefly talk about the asymmetric diabatic heating around the tropical cyclone. Well, this is a very, very simplified story, so maybe we need to consider more if you are interested in, but let me simplify the things. When we assume that the easterly wind in the lower troposphere or lower level boundary layer, lower levels like this, and then at the same time we assume that the westerly wind is blowing in upper air. This is a large scale condition is like this. Okay. In that case, upper level wind minus low level wind is called as the vertical wind shear in the field of tropical cyclone studies. And in this case, from left to right is a vertical wind shear direction. And the downshear side, we expect the stronger convection because, as you can see here, stronger inflow occurs and then strong outflow occurs. So it is, this kind of stronger convection is expected in a downshear side. Of course, the flow story is not so simple. Like tropical cyclone has this kind of circulation, and also we need to consider the balance. So it's a bit complicated in a real situation. It's bit more complicated, but as a rule of thumb, active convection is seen in the downshear side to the downshear left side. Okay, So how about this binary? Okay.
Go back to the previous slide.
Okay.
That environmental wind is true everywhere, so it's
So
all
everywhere, yes,
left
yes,
side.
everywhere, yes, everywhere. Thank you. So let me check the low pass filter, large scale wind field for our numerical simulation cases. Okay, so left panel indicate the upper level wind and low level wind. You see that the red arrows indicate in upper level there is a clockwise circulations. And in the lower levels, now of course if we focus on the smaller scale, here is the cyclonic circulations like this, but if we filtered the smaller scale features, the large scale features is like this. So counterclockwise, anti-clockwise circulation. Okay, so vertical wind shear is defined as the upper level wind minus low level wind. So vertical wind shear is like this. And then we can expect the stronger convection outside from the counterpart tropical cyclone. So that explains the tropical cyclone move away from each other. Okay, some people are wondering why clockwise circulation is seen in the upper level and counterclockwise circulation is seen in the lower level. So I think this is a simple schematic diagram. As you know, if we consider a single tropical cyclone, a cyclonic circulation is like this, and then in upper level, due to the friction in absolute angular momentum should be decreased near the center. So outgoing flow is usually has the anticyclonic and clockwise circulation after the decrease of absolute angular momentum. And this anticyclonic circulation has a size of about Rossby's deformation radius at that altitude. So just about 1,500 kilometers is a typical scale. And then now we consider the second tropical cyclone. If we consider the sum of these two vortices, the flow is cancelled out in the middle. So we expect this kind of large scale circulations in a lower level and large scale anticyclonic circulations in an upper level. Yeah, of course, if you are specialist on this subject, we need to consider local inertial stability at each location, but we skip it. Well, this gives the vertical wind shear to each other. And then it further gives the asymmetric diabatic heating outside from the counterpart tropical cyclone. And then, it modifies the tropical cyclone motion. Well, it takes some time to develop. Well, originally, we just put two tropical cyclones. At initial time, there is almost no vertical wind shear. But, as I mentioned to you, outflow tends to become anti-clockwise circulation in a time scale of 1 over f. So, in that sense, after a few days, our vertical wind shear becomes stronger and stronger, and then it makes a change of the tropical cyclone motion. Except, two cases get merged. Okay, now I showed you when two tropical cyclones are located very closely. In that case, they get merged, and we saw the conventional Fujiwhara effect if two tropical cyclones are located very closely at the initial time. So what happens is, in that case, if two tropical cyclones are located very closely, it means the strong wind blows to each other. So the impact from the advection dominate the situation. So this horizontal advection is much stronger than the contribution of asymmetric diabatic heating. But if the initial separation distance is sufficiently large, we expect horizontal, not only horizontal advection, but also asymmetric diabatic heating are important. To make sure this finding is true or not, we turned off the diabatic heating. This is results from these two experiments for the initial separation distance of 8 degrees. So if we include the diabatic heating, the two tropical cyclones shows the at first counterclockwise rotation, but they keep away from each other. But if we turn off the diabatic heating in a numerical model, they pretty soon get merged. So which supports the asymmetric diabatic heating impacts the separating motion. Okay.
So I'm guessing in simulations like this, probably you turned off friction.
Mm-hmm.
Yes.
What do you mean?
Do you turn off the friction in the back? You must, because otherwise they would just
Right. So yeah. I think I did that. Yes.
Yeah. And also, how strong are the initial vortices?
Okay, maybe you can check my paper, but actually, initially not so strong, maybe 990 hectopascal at the initial vortex, but later on it becomes 950 or something
Right,
like
but
that.
with no diabatic heating, you must.
Yeah. In that
Are you
case,
starting with a stronger vortex? That's what I would do if I were them.
yeah, I think I'm sorry, I do not remember, but we definitely remarked that issue in our paper. So maybe let me check later.
Talk about this.
Okay, so this is a schematic illustration. We expect the upper level anti-clockwise circulation. Clockwise circulation, anticyclonic circulation in upper level, and low level cyclonic circulations, and particle wind shear comes out after several days, and then it contributes to the asymmetric diabatic heating, especially which are much active in outside from the counterpart tropical cyclone, and then it modifies the tropical cyclone motion. Okay, so now we would like to check this really happens in the real atmosphere. So we compiled the DRTCs whose separation distance were less than 2,000 kilometers in the western North Pacific. So a pretty large number of cases are analyzed here. We use the ELA5 for the atmospheric analysis. And just reminder for you is just we need to be careful about the coordinates we took. And in our analysis, we employ this kind of axis mostly. So in this axis, we took the center as a tropical cyclone center, and then x direction is directing to the counterpart tropical cyclone. And then y-axis is the left of x-axis. So just from this tropical cyclone, x-axis, x direction is this direction, and then left of x-axis is y-axis. And then we call each quadrants as a down counterpart left or up counterpart right or something like that. And it means if tropical cyclone moves to the positive x direction, it going to approach to the counterpart tropical cyclone. And then if it goes to the negative y direction, it means that anti-clockwise rotation with respect to the center point. Okay.
Did you, in your simulations, did you make one tropical cyclone stronger than the other?
I did that in the idealized simulations, yes. yeah, just as I mentioned, if one is bigger and one is weaker, the more impact from this one is this one. And then this one doesn't much impact on this one. Okay.
In your statement, the figure you had a little bit before, the simulated reflectivity, was that a point further out in time? Because it seemed like the reflectivity was quite equivalent between the two vortices. It seemed they were similar in strength. If you initialize it with stronger.
Yes. So today I only show the results for identical thesis. So in this case, so I didn't discuss about one strong and one weak cases for my idealized simulation cases. But of course, definitely in the real atmosphere, one is stronger and one is weaker.
Yep.
So I decided to call TC1 for larger saturation, and TC2 is for weaker or smaller saturation. Okay. But this is the basically this is the track deviation with respect to a binary center for all the cases. We classified by the separation distance of all the cases. If the separation distance of two vortices less than 1,000 kilometers, in that case, you see the positive x and negative y, which means the two tropical cyclone tends to approach an anti-clockwise rotation. And when a separation distance is between 1,000 kilometers to 1,500 kilometers, in that case, negative y component is still clearly seen, which means the anti-clockwise rotation is seen in this group. And more than 1,500 kilometers, there is almost no track deviations with respect to the binary DC center motion. So you might see, there is no interaction between two TCs. But later on, I will explain, no. These two TCs have some interactions, but it cannot be seen in the track deviations. Okay, so first, let me confirm the particle wind shear is similar to what we saw in an idealized simulation. This is the result. Yes, this is non-filtered wind field, but you see that in the low level wind is cyclonic and upper level is anticyclonic. So as a result, particle wind shear is strongly anticyclonic. So which is corresponding to the idealized simulation. Now, of course, in reality, there are many disturbances other than tropical cyclones. So we need to consider those disturbances. But even after subtracting the climatology, this particle wind shear are still robust. So which means these particle wind shear can be, at least part of this particle wind shear are coming from these binary tropical cyclones themselves. And then this is a diabatic heating asymmetry. Again, the x-axis represents the direction of counterpart tropical cyclone. You see that stronger diabatic heating occurs in a UCL quadrant, or some are seen in UCR quadrant, but which means stronger convection occurs to the left and back side with respect to the counterpart tropical cyclone. This is also consistent with the idealized simulation. So convective asymmetry tries to separate two tropical cyclone, right, and try to stop the anti-clockwise motion. Okay, so this is a PV budget analysis. Let me focus on the 850 hectopascal analysis for the separation distance between 1,000 kilometer and 1,500 kilometer. In that case, PV tendency is a positive value in a negative y area, and positive PV tendency is seen in negative y regions, and negative PV tendency is seen in positive y region. So which means tropical cyclone tends to move to the negative y direction, counterclockwise rotation. But their breakdowns are very interesting. Horizontal advection tries to move the vortex to DCL direction, which means most tropical cyclone is advected to the approaching direction and anti-clockwise direction. But you see that asymmetric diabatic heating resists that. So the contribution of asymmetric diabatic heating tries to stop anti-clockwise circulation, and then tries to make the vortices separate. So as in the idealized simulation we saw. But I think, of course, it's a little bit different because in this case, horizontal advection wins the heating, diabatic heating, but the direction of their behavior is consistent with idealized simulation.
So,
Okay.
can we say in conclusion like diabatic heating always compensate or opposed to horizontal advection? Because you see those two, they kind of opposite to each other. It's like if you calculate like you are doing the budget here, you are seeing the total like dou PV or dou T, like change in potential vorticity is sum of these three terms, and the main balance is between horizontal advection and diabatic heating. Because if you sum these two, it mostly cancel out. You got it? So I'm saying like mostly diabatic heating compensate the contribution from the horizontal advection.
So I'm sorry, you have any question? No?
Yeah, my question is it always the case or just it is the particular scenario?
This is the for composite of all the cases for the separation distance for this one.
Yeah, so this is from over many storms.
Yes.
Yeah, because the pictures are so clean.
Yeah.
It looks like it was from the idealized run.
Right.
But that's actually average over many cases.
Right. Yeah, of course, individual cases are not like that.
Oh, okay. This was my question.
It seems like your PD budget, it's not balanced, right? Basically, your life side is the PD tendency, but you sum up all these right-hand side three terms, looks like they're not, if you sum up the right three terms, they wouldn't match with the left.
I'm sorry, I cannot.
Your budget is not balanced. Have you checked the balance? Like, for instance,
Balance, yes, I checked. And almost, the sum of the right-hand side is almost same as the left-hand side. That's what you mean? Yeah. So that round reviewer pointed out that, I think some 5 to 10% difference was seen, but I think it's not significant. So I think we are pretty sure.
Advection and diabatic heating compensate, and there is something shear from the advection getting the left hand side.
Right. So I think I'm sure that the pretty right-hand side is a good breakdowns of the left-hand side. Yeah. Okay. So this is a kind of vertically averaged contribution of each term.
And sorry, can I ask?
Okay,
the
sure.
previous one you showed just for the surface, right?
What? Excuse
In the
me.
previous slide. Oh, sorry. Yeah, it's okay. All good.
It's okay.
Yeah.
Okay. So this is the some kind of vertical weighted mean for the contribution of each term, and you see that horizontal advection tries to make the vortex approach and rotate to the counterclockwise direction, but the diabatic heating asymmetry tries to resist that, and as a result, the final direction of motion is determined. Okay, so maybe some are interested in the PV structure and diabatic heating, but I can skip here. Maybe as you expected in a that just down shear side and down shear left side. Okay, so what happened if two tropical cyclones are located closely? In that case, yes, as I mentioned, for the idealized simulation, the PV budget is almost explained by the horizontal advection because they are located closely. So the motion is dominated by the horizontal advection, mostly explained by horizontal advection. Interesting result is this. PV budget for the two TCs separated between 1,500 kilometers to 2,000 kilometers. In this case, as I show you, there is almost no track deviation with respect to the 2TC center. But there is some horizontal advection and diabatic heating, which means, okay, so 2TC is separated about 1,600 kilometers or 1,700 kilometers. In that case, the motion is, in terms of motion, just we do not see any particular rotation or approaching motion, but still they have some interactions. This tropical cyclone tried to move this vortex in this way, but it was resisted by the vertical wind shear related, asymmetric diabatic heating. So when this, wind related to this tropical cyclone tries to move this direction, but it was resisted to the cloud genesis outside from the counterpart tropical cyclone, like this. So as a result, we do not see the track deviation with respect to the binary center point. And we checked the dependency on size and duration. If both TCs are small, as you expect, the horizontal advection is weak, and diabatic heating asymmetry impact is also weak. If two TCs are both large, horizontal advection becomes large, and asymmetric diabatic heating contribution is also large. And interesting thing is like this here. Young couples, if you consider young couples, the positive x direction means black vector, have component positive x and negative y. Positive x means they tend to approach to each other and counterclockwise rotation. And for old couples, here the duration is defined as the time since two TCs are within 2,000 kilometers. Okay, so if a couple of binary TCs are sufficiently old, in that case, you see that asymmetric diabatic heating contribution become much stronger, and then you see now negative x, black vector shows the negative x component and negative x, negative y, so which means going slightly away from each other. By the way, I met my wife 20 years ago. So if I and my wife were tropical cyclones, we get closer to each other when we were young. But time goes by, vertical wind shear are generated by our system of binary tropical cyclone themselves, and then some vertical wind shear occurs and some clouds are generated outside, so they tend to be separated, right? Then fortunately, I and my wife are not tropical cyclones. So I and my wife keep good relationship and keep distances between us. But anyway, so that's the story. Okay, so initially there is no such strong impact from the asymmetric diabatic heating coming from the binary tropical cyclones themselves. But later on, a system of binary tropical cyclone can generate the particle and shear, which can modify the tropical cyclone track themselves, and then they tends to be away from each other in a later period. Okay, so I also checked the geographical differences because some are curious about the impact from the large-scale flows, but actually the result is pretty robust. Basically, we see UCL, strong convections in the UCL dimensions, quadrant. Yes, we see some changes in the South China Sea area, but we can explain this by using the climatological vertical wind shear. So I think the findings of us are pretty robust. Okay, so these results were already published in 2 papers. One is for idealized simulation, and the other one is for the real case analysis in the Western North Pacific. If you are interested in, just please check out these 2 papers. Okay, so that's all for my talk. Thank you very much.
Okay, I will now walk around with the microphone so the Zoom.
So again, the last results we were showing were composites over real.
For real cases, yes.
Excuse me, and you have a duration condition. What's the boundary between, first of all, duration just the lifetime of the storm?
Do you mean this one?
Yeah.
Okay, this was, I think I remember maybe 1 day or a little bit more than 1 day is threshold.
Oh, only 1 day.
Yeah, more than 1.5 day. You can group in the data set into this group.
I see. So you need more than 1.5 days from the beginning of the storm, or 1.5 days of being that distance apart?
Yeah, sufficient. The 1.5 day is enough to make two tropical cyclones go away from each other.
No, what I'm saying is, what you call an old couple, how old are the storms?
How old tropical cyclones are themselves?
Yes.
I haven't checked, but what I said that old means the duration since the couple.
Right. That's what I mean. So this is
so I didn't check.
which they were interacting with each other.
I didn't check the tropical cyclones ages themselves. So yeah. Thank you.
I have a question about what caused that asymmetric distribution of diabatic heating. Idealized case, right? You saw the separation of 2 vortex. So the convection on the upper side is kind of like on the outer side of the storm, like on the side. But what did the shear cause that, or? But then in your diagram you show the shear direction is important, right? So basically, down shear side, your convection is stronger. But is that shear direction different over those 2 storms? So what was
You are asking for the real cases or idealized cases?
Either one. It's very. Mostly the idealized. If you go to you have a movie.
Yeah. Okay. So I think. I'm sorry. I do not bring a clear result, but basically, what we saw is basic, things like downshear or downshear left. That's a very basic thing. Just maybe not your question.
Sorry, if you go back to another one. The one you show the cartoon, like you show the movie of your simulation. The idealized.
This one? No.
Oh yeah, this one is okay. You see those two purple arrows, right?
Right.
So those are, I mean, you see the convection location is different, very different in these two storms.
Right.
So what causes, you are saying the shear causes this asymmetry of that?
Yes, we think so, yes.
So that means the shear direction is different over the two storms?
Shear direction is, yeah, like this way, right? So you see, in this, maybe you can consider this circulation in this way and this way. Vertical wind shear from, in this case, northwest to southeast, right here. And here is, yeah,
Thank you.
southeast
I
to
think
northwest,
My
right?
question is basically, so the vortex interaction cause a shear direction difference too?
Right.
Besides the other.
Mm-hmm.
Thank you.
Yeah, great presentation. I learned a lot. My question is with the D08 case, which showcased the highest magnitude wind shear. You showcased that at about 16 meters per second of wind shear. That's quite significant.
Mm-hmm.
So I'm wondering in your idealized simulations if you saw obviously the stronger initialized vortex can have a larger influence in terms of wind shear on the weaker vortex in terms of the circulation sizes. You see in your simulations the weaker initialized vortex dissipating due to the vertical wind shear influence of the stronger vortex.
Yeah, I think it's very interesting question, but in this case, we fixed the sea surface temperature. So just the tropical cycle intensity adjusted to, MPI. So we cannot test that, but maybe if we try the, different SST conditions, maybe we can clarify that impact. But I didn't that.
Thank you.
So in the real world cases, how did you actually define what the separation distance was? Like, since in the idealized, they start out 1,000 kilometers apart from each other.
Mm-hmm.
In the real world, they're moving. How did you decide when you would classify as a certain?
Yeah, just maybe rounded numbers, but yeah, and also if we use a 500 kilometer for the minimum case, it doesn't have many cases. Doesn't even, only a few cases are inside. So just at least we need to have a good number, sufficient number for analysis, right? So just from that perspective, we decided 1,000 and 1,500 and 2,000. And another reason is just many previous papers said that interaction is seen 1,500 kilometers. So I think beyond 1,500 kilometers have not been investigated previously, I think. Not much. So because I suppose many people are looking at the track deviations. So almost no track deviation. So they assume that there is no interaction, but it's not true, as I said. So I think the more than 1,500 kilometer, the analysis is very new, quite new, of our one of our new stuff from out of our big works.
So for the real world, where you have background flow, like
Right.
yeah, the vortex is actually moving.
Right.
How do you define the initial separation distance?
Initial separation, no, we didn't define the initial separation distance. This is just separation distance. So in a real,
This evolves over time?
Yeah, in each group. So in this case, in a real world cases, we didn't use the initial separation distance, just the separation distance.
Okay, so like one binary interaction,
Right.
you go through all multiple of these categories.
Right.
Okay.
So that's a trick. So a little bit slight difference between idealized and real cases.
Yeah, back to the young versus old, young attraction, old repulsion. If we take that away from time domain for a minute, does it imply there's an equilibrium distance at which they neither attract nor repel? And would that predict an increased frequency of occurrence of that distance? And then could you go into observations and show that there's an enhanced frequency of occurrence of the distance that corresponds to the equilibrium between your young and old? Is there an equilibrium underlying this that might make a prediction that you could test with observations?
Yeah, thank you very much for your suggestion.
Middle age.
Yeah.
Is there a comfortable middle age here?
Thank you very much. So yes, again, well, so I think the just very conventional Fujiwhara effect concept. Just if we prepare two positive vortex regions, they just get merged, right? But what we have introduced is initially they can show the clockwise, the counterclockwise motion. But later on, when the particle wind shear effect is more activated, in that case, the direction of motion can be changed. So that's our comment. So I'm not sure is there any equilibrium, since in our simulation, particle wind shear tends to become stronger and stronger in time. So from that point of view, I'm not sure there is an equilibrium, but maybe we can consider. Yes, thank you very much.
Do we have questions from the Zoom audience? If yes, activate your camera and microphone. But I don't see anything. So thank you.
Thank you very much.
Presentation. Thank you all for coming, and come again in 2 weeks when I think we have another visitor in 2 weeks.
All right, thank you, Roland.